Okay, here's our example using reaction quotient. Say you make 0.23 mole of H2, 0.146 mole of I2, and 1.98 mole of HI in a 1 liter container. Here's our reaction. We've seen this before. K, our general value for K at this temperature, which is not specified, is 50. All right. But is this reaction at equilibrium? Note you put in reactants and you threw in some product too. So did you happen to throw in the right amount so that this reaction is actually at equilibrium? Question 2, if not, if the reaction is not at equilibrium, which direction must the reaction go from this point? Must it go to the left to make more reactants, or will it go to the right to make more products from this point? All right, first off, threw you a little bone here. We've got a 1 liter container. So if we have 0.243 moles of H2 in a 1 liter container, that means we have 0.243 molar H2. Perhaps on homework assignments or quizzes and such, I will put it in a 0.25 liter container. Then you'll have to do just a little extra math in order to get the concentration. All right. But because it's a 1 liter container, we know we have 0.243 molar H2, 0.146 molar I2, 1.98 molar HI. So question, are we at equilibrium? We answer that by figuring out the reaction quotient. We do not know if we're at equilibrium, so we're doing the reaction quotient Q. Q equals concentration of HI squared times concentration of H2 times concentration of I2. 1.98 squared, make sure you square it, times these two values, and we find Q equals 111. However, we found that although Q equals 111, our equilibrium constant is 50. These two numbers are not the same, so we're not at equilibrium. We also see that 111 is much larger than K. Q is greater than K. Therefore, the reaction will go to the left towards reactants from this point. And very, very important here, our equilibrium constant is 50. It has a value of 50. So the reaction in general lies to the right. The reaction lies to the right. We have more product than reactant at equilibrium. However, it turns out when you threw in that 1.98 moles of HI, you threw in too much product. Even though this reaction does lie to the right, because K is 50, there's still, at this point, because you threw in that product, there's too much product, so the reaction must go to the left from this point. Cool. Okay. And that's reaction quotient, not too bad. Let's now look at the other type of equilibrium problem. When you know the equilibrium constant and you're trying to find the equilibrium concentrations. You know what the constant is, you need to find the concentration of equilibrium. Ice tables is the key. Ice, ice, baby, we need to do ice tables. All right. So here's an example right here. Say you have a reaction. Here's a reaction at 200 degrees Celsius. You find that the equilibrium constant is 24.0 for this reaction. A molecule called cis-stilbene is in equilibrium with the molecule trans-stilbene. All right. At the beginning of the reaction, you have 0.850 molar cis-stilbene. You do not have any of the trans. Question, once you reach equilibrium, though, what are the concentrations of the cis and trans stilbene? We know our equilibrium constant. We want to get the concentrations of cis and trans stilbene at equilibrium. Well, we set up the ice table. I always like to start it with the equation. I put the equation up here. Cis stilbene in equilibrium with trans stilbene. Here's our cis, here's our trans. I need to know their concentrations. ICE, draw the line. We know our initial concentration of cis-stilbene is 0.85 molar. Our initial concentration of trans is 0. But now, in our ice table, we always looked, okay, how much cis-stilbene went away? How much trans-stilbene came into being? We do not know that. We don't have that information. So I don't know how much cystibine went away, so I'm going to put minus x. Minus because I know some of that cystibine did go away. It got converted into trans, so it's the minus x because I don't know how much it is, so I'm putting x. However, our stoichiometry is 1 to 1, which means for every mole of cystibine that goes away, 1 mole of trans-stilbene comes into being. So if the concentration of cystibine drops by x molar, the concentration of trans-stilbene increases by x molar. Our stoichiometry is 1 to 1 here. Note if it was 1 to 2, it would have been 2x over here. But it's not, it's 1 to 1. So then at equilibrium, I have 0.850 minus x as my concentration of cystibine, and x as my concentration of trans-stilbene. I can write down my equilibrium constant expression, K equals concentration of trans divided by the concentration of cis. And I can start putting in my values here, or else what I can put in, my equilibrium constant, I know that. In these reactions, I know this. It is 24, so I put 24 in there. What's my concentration of trans-stilbene at equilibrium? It's x. What's my concentration of cis-stilbene at equilibrium? It's 0.85 minus x. Put that down in there. And so once we get to this point where we have this math, the rest is just math. But the two things we need to do, first is solve for x. Once we solve for x, though, we're not done. We need to use that x value to solve for the concentrations of our cis-stilbene and our trans-stilbene. All right, to the algebra class we go. We're solving this for x, so, okay, multiply both sides by 0.85 minus x. And so, yeah, 24 times 0.85 minus x equals x. Okay, minus x equals x, got that. Do this math, okay, we get that right there. Collect like terms, so we got 20.4 on this side. We had to add 24x to both sides, so that gives us 25x. X equals 0.816. Now, the math gives you x equals 0.816. However, we know that we are solving for concentrations, molarity, so we know this is x equals 0.816 molar. Okay. Now, note that now that we've got 0.816 molar, we're not quite done. We need to solve for concentrations at equilibrium. Turns out the concentration of trans-stilbene at equilibrium is x. So we know our concentration of trans-stilbene is 0.816 molar. But our concentration of cis-stilbene is 0.850 minus x. So cis-stilbene concentration, 0.850 minus x, well, that's 0.850 minus 0.816, that equals 0.034 molar. And now we have those concentrations. And as a little internal check here, you realize that what would happen if this number, x, was larger than our initial concentration? You'd have got, what if you ended up with a negative molarity? Then you've done something wrong. You can't start with a certain value and end up with a negative amount of that stuff. So you'd have done something wrong at that point. All right. In the next video, we're going to go through a couple more examples because I hate to break it to you, the math here was the easy math. Let's look where math starts to get a little bit more difficult. I'm sure you can do it. I'm sure you've done it in your algebra classes, but it gets a little trickier.